all. Thank you very much for the kind introduction, Marius. Can you all hear me? I have a tendency to move up and down. I cannot really stay in one place, but if I'm over here, can you still hear me with another microphone? Good. I'll try to be in my best behavior. So, given that these were about challenges for computational intelligence, I had two options. One was to talk about what I've done, which I could do blindfolded and half asleep, which I am, due to time jet lag. The other is to say, well, what am I going to do in the future, which is always more challenging, right? I think a great American philosopher said predictions are difficult, especially if they're about the future. And that philosopher was Yogi Berra. For those of you who know, Yogi Berra was a coach, baseball coach, right? There is a confluence of disrupting technology, that's cloud computing. There is a re-emergence of analytics as being a key differentiator for delivering new services in a new environment, which is called the Internet of Things, or Industrial Internet. And there is another emerging behavior, which is crowdsourcing, in which people are actually part of the solution. And in fact, when when human agents and computer agents interact together, it's called crowdsourcing, or everybody as a service. And I thought that that intersection was more the future context in which business and service will take place and will be delivered. And this will also change the nature of how we do research. Okay? And so that's why I call it How to Destroy My Job. Because I thought that the best way to describe this was by taking, so it's always easy to predict the future when you look at the past and you're trying to say, okay, now, how is this going to change given this new context, right? We engineers take derivatives to extrapolate. But it was basically saying, how was my job 20 years ago? How was 10 years ago? How is it now? How will it be? And that's my sort of a personal retrospective journey, and that's what I call How to Destroy My Job. So the outline of the menu of the day is very simple. There are three components. I'm not going to spend too much time on the first two. I'm going to talk a little bit about crowdsourcing because probably is the least known of the three. And then look at the intersection, at least of two of the three components, and then how it affects me, how it's changing my role, and how I believe your role will also be changed. And then if I don't have enough time to discuss it now, we will do it through the roundtable later on. What are the challenges that we face as a community in terms of this new paradigm that exists, that is developing? So this is a great picture of cloud computing. I got it from the IEEE. I have always the best pictures. And it's, I think, the inevitable answer. It's unavoidable, just like people who decided that internet was a thing, a fad, right, in Internet 1.0, and it created a backbone for communication. And then Internet 2.0 became change the way businesses are rendered. So e-commerce started with Internet 2.0. Internet 3.0 is machine connected to machines, generating large amount of data, and so the term big data. And the fact that now you have elasticity in provisioning nodes, processing nodes, and that's what the cloud is. And all you need is a credit card. You don't need capital expenses. You don't need to buy your service. You go to Amazon Web Services, and you rent as many processors as you need for as many hours you need, and you pay by the drink. Right? That is what is changing. So a lot of small companies do not need huge capital investment to buy servers. They just need OpEx rather than CapEx. And just to keep it brief, one could give a whole talk about cloud computing. That is not the intention, but I want to just specify a few things. There are infrastructure as a service is sort of a bare model. Let me see if I can get the mouse. Well, doesn't matter. You can read. Oh, here it is. Where you're just buying renting the hardware, and you put everything else on top. platform as a service assumes already some programming environments and applications in it. I want to focus on the last two, service, software as a service, and human as a service. Right? Where software as a service would be providing, for instance, analytics as a service, and human as a service is crowdsourcing. Right? And these are examples for if you don't know what crowdsourcing is, just go to Amazon Mechanical Turk, and it's probably the largest market for crowdsourcing. So that's a good example of that. Anyway, the slides will be made available, and so you can get all the references. You don't have to scribble it now. So I just wanted to tell you, it's here. It's unavoidable. It's like a tsunami. Just get a big surfboard because you have to ride it. Analytics is the secret sauce, is what we've done for many, many years. We know how to develop models. There is a methodology for that. What I'm telling you is that methodology does not scale up. It does not scale up in the number of models that you need. It does not scale up in the volume of the data that you have to deal with, in the throughput when the data is streaming that you have to handle. And you cannot handle big data unless you have elastic provisioning of nodes, which is the cloud. So you have to start thinking about how to do research in the cloud. So then you can deliver service from the cloud, and there will be new business models that will facilitate that. I mean, it's happening in the States already. It's happened for the past couple of years. And I can probably skip this, but just to give you an example of what I mean by data-driven models is whether it's structured data, such as time series or categorical data over time, versus unstructured data, which is mostly text. And with text, you can do search. You can go one step above, which is bag of words. You can go one step above, which is the translation of this text into 3 tuples into a database, which is what Watson did from IBM. Or you can go one step deeper, but more manual, which is creating semantic ontologies out of that. And again, one could spend a whole day talking about this. I'm just saying this is the second component. In the case of GE, we have many assets. For instance, we're monitoring aircraft engines on wing while it's flying, and you get telemetry. And by telemetry, you get this time series from the sensors, or you get event codes, which is categorical data. And depending on the type of data, whether it's categorical or time series, you have different techniques that we've used in the past, okay? When we're dealing with simulations, that's basically trying to capture domain knowledge. So this is a domain knowledge about thermodynamics. And if I know the flight envelope in which I'm running an engine, and I have some idea about the deterioration level of its main components, I can tell you which sensor reading I should get. And then comparing that with the actual sensor readings, I can analyze the deltas, the residuals. And that's when we're applying data-driven approaches to it. So this was just a very quick synopsis of 2 of the 3 components, right? The cloud is there. It's an opportunity, or be a challenge if you don't adopt it. Analytics, these are analytics of the past. We have to change the way we're doing analytics in this new context. There is a third component, which are the people, right? The crowd. And the concept of crowdsourcing, also referred to as collective intelligence, starting in 2004, when there was a book called The Wisdom of Crowds by Surowiecki. I always mistreat Eastern European names. I forgive. Ask for forgiveness already. But that was it was an interesting book. It basically said if you have a diversity of opinion, this is a key word, and you can collect those opinions independently, so you don't have group thinking and swaying of opinions. And then eventually you aggregate those opinions, you get very appropriate results. It goes back, perhaps the earliest enterprise that was built out of crowdsourcing was a T-shirt design where the crowd designed the T-shirts. The crowd voted on which T-shirts ought to be manufactured. The crowd marketed and did publicity, and then they ended up buying it. And in some cases, they also funded. So this was in 2004, right? If you go to again, I'm not spending too much time, but in 2008, there was a book called Crowdsourcing by Jeff Howe that talks more about collective intelligence. There's a whole group at MIT, at the Sloan Business School, devoted to collective intelligence, in fact. And it talks about how the crowd could create or could decide or could fund things. Again, it's it's sort of a refinement, a new view. It talks about innocentive. How many of you are familiar with innocentive? Not many, right? In fact, I don't see a single hand. Innocentive is a way of doing R&D via crowdsourcing. So I'll have a slide in the next slide. And the question is, how do you motivate people to participate, and how do you retain them? And there are many ways of doing it. Money is not just the only one. Many times it's fame and glory and credit within your community, prizes. Other times it's the equivalent of micropayment with points similar to loyalty cards, where eventually you can redeem the points for something. But in the meantime, you're also exposed within the community as having cracked this particular problem. Just to give you an example of what innocentive is, you go to innocentive.com and you find an interesting question, if I can read them here. Sort of, how can I use an augmented camera, so a camera with augmented reality, or something about perfumes and molecules for chemical engineers who can solve that. So there are people who say, hey, I have this problem. I'm going to put a small award. If you have any idea, which is either IP3 or I can use the IPs to implement the solution, go ahead and submit it. And you have a large number of contributors submitting to this. So I'm not saying that it replaces R&D, it augments R&D companies. So, and finally, in 2012, this was a book that really motivated me. It's called Reinventing Discovery by Michael Nielsen. He talks about how collaborative tools are used to augment the collective intelligence. And he uses many examples. The polymath problem, which was on the density-Hales-Hewitt theorem. Density-Hales-Hewitt theorem is basically in a 3x3 matrix, which is the simplest to tell, is how many points I can put in each cell of this matrix without creating a line, right? And clearly the number is 6, because as soon as you put a 7th, you'll be connecting some lines. But do that on an n by n in many dimensions, and it's not trivial anymore. And that's what these mathematicians were trying to solve. So there is an interesting quote by Tim Gowers. Tim Gowers, by the way, received the Field Award, the Field Medal, which is the Nobel equivalent in mathematics. You all know why there is no Nobel Prize for mathematics, right? Nobel's wife had an affair with a mathematician. And so Nobel decided there wouldn't be any prize for mathematicians as the field. And so he basically started with a blog and having other mathematicians contributing to it. And basically he said that polymath process is to normal research as driving is to pushing a car. So that's how much it was amplified. They end up solving not just the particular theorem, but the most generic problem of which that specific problem was an instance. And this goes on. In 1999, Kasparov versus Award was an interesting chess match with Kasparov on one play, on one side, and the whole world on the other side. And the whole world was suggesting plays. There were some coordinators who were accepting the submission and making the decision, but more importantly, there was a publicly accessible analysis tree showing moves and counter moves. That is, they start digesting the analysis and sending it back to the crowd. So you always had an amplification of that knowledge. And this is just an example of how tools can work on that. And finally, and because I have to carry on, otherwise I'll never finish, to complete this part, there's Galaxy Zoo. And Galaxy Zoo, let me just give you an example, is a way in which over 250,000 people are classifying the shape of galaxies, right? Then you had Galaxy Moon, where people start looking at the diameter and shape of craters on the moon. And this is called citizen science. Okay, so you have people participating in tasks that have been packaged in a way that can be parceled out with a minimum amount of information and skill sets. But that is not the only way of doing crowdsourcing. You may also do crowdsourcing internally in an organization with your own expert, where the talent skill is much higher. The problem has not been parceled out very cleanly, and they're solving the problem together through interaction, or they're solving part of the problem, and the other part, maybe the heavy lifting is done through computers or an analytic engine. This concludes the three components individually, right? Now I want to look at the intersection of them. Unfortunately, someone already did it for me, and that's the AMP or AMP lab at UC Berkeley, where A stands for algorithm, M for machine, and P for people. And it shows how different entries, right, fall in this space. And finally, how they're looking at the intersection of all three. So I strongly recommend you that you go to their site. And basically, in a few words, they're saying machine learning, if you're doing it in the cloud, should be such that you understand at the meta level the complexity and performance of the algorithm that you're using, so you can use anytime machine learning. In other words, you can say, if I allocate 100 processors, how much time do I need to reach this confidence level? Or if I want to fix a time for a given number of processes, which confidence interval would I achieve? Okay? And the idea is that, of course, you have to create some kind of, to construct your algorithm in a way that are anytime. So evolutionary algorithm is a good example of that. You can always stop and see what is the last generation output. But what you like is some kind of a monotonically non-decreasing behavior of your confidence intervals as you're allocating more resources. The machine is all about creating, making the data center a real computer. So on top of a typical operating systems, Unix or Windows or whatever, or Linux or whatever you have, they have mesos, and then they have a whole slew of tools to do rapid data ingestion for streaming, in-memory query, caching data sets so you don't have to recreate the data every time that you're iterating, which is what MapReduce needs to do, and so on. And finally, people, the P for AMP is people, or crowdsourcing. They have a wonderful application called CrowdDB. And CrowdDB is basically removing the assumption of closed word in a database. When you put a query against a database, you write your SQL query. You assume that all the data is in the database, right? You cannot get anything which is not in. So sometimes you get a null query, or sometimes you get some incomplete data. In this case, the system is connected with Amazon Mechanical Turk, and it says, whatever is not known to the database, I'm going to parcel it out to the crowd. There is a HIT manager. HIT stands for Human Intelligent Task, that handles a payment to whoever is contributing to that. There is a way of showing the query. There's a way of doing quality check on the output, and then it's incorporated back as a three-tuple or a series of three-tuples into the database. The query is answered, and that information stays in the database. So again, it's where the crowd is now a complement to the machine, right? But you expect most of the heavy lifting to be done by the machine, but the crowd complements. Another great example of crowdsourcing is if you want to have a translation of a document from L1 to L2, and you can use Google Translation or anything else, right? But then you want some quality control on the translation, some quality assurance. You want to make sure the translation is really perfect. How do you do that? You cannot write another program, because otherwise you would have written that to begin with. You take the output of a Google Translate, and you pass it out to a crowd who basically makes comments and refinements to the translated document, right? And that's an example of crowdsourcing. Okay, enough of talking about the intersection of the three. Let me just focus on the intersection of the two. So I just want to whet your appetite about crowdsourcing. Now I'm spending most of the time on analytics and the cloud, so we know where we're standing. And these guys came up with a great idea. It was nicknamed by Businessweek in January of this year, the Fight Club for Geeks. I don't know if you've seen the movie Fight Club, but basically this is where geeks slug it out, right? Where geeks compete for prizes and for recognition. So there are many competitions. Perhaps the most significant one is the one by the Heritage Network provider, Heritage Network Prize, that has to do with hospitals and length of stay. So when you have inpatient in a hospital, you really want to forecast the length of stay. How many days will this patient be in? Because this is the same as forecasting your load in power systems, right? You then can optimize your load generation through your generators and whatnot if you have a load profile. The same with hospitals. If they have a good estimate of length of stay of each patient, then they can optimize the capacity in terms of beds and equipment that they have and the allocation. And what's interesting, I'll just give you a couple of synopses. This is about credit score. And this is only worth, what, $5,000, and you have 1,300 players. And for the Heritage Provider Network, it's a $3 million. This is really big, over 18 months, right? And you have 9,000 entries. So there was a law, I think it was called Surgeon Law, that says 90% of that is junk. Right? If you remember, it was in one of my second slides in the crowdsourcing. That means that 10% are still nuggets. Now, most of these competitions, first of all, an aside, and then I'll try to get to my part, but I think this sets up the context, which then I'll be using in the afternoon roundtable. Most of these, how many of you know about the Netflix competition? A few, at least. Good. So Netflix predated this, Kaggle.com, and Netflix says, I'm going to put $2 million for whoever comes up with an algorithm that can predict the next request of movies, right, and can do 10% better than what we can do now. But Netflix was not a competition. It was an experiment in human evolutionary algorithm. Because as soon as you had an entry, you were scored, you were getting a grade. And everybody could see your entry and your grade, right, your fitness function value. And then if Shane was very good, has a good entry with a great grade, mine was lousy, I can look at Shane's grade and Shane's entry and says, this is a good idea, let me modify it, right? And so it's like a mutation of his entry. If I win, we'll share the prizes, no problem. It's not a plagiarism. But it was not, they were not independent entries. Eventually, you converge to a small number of good models, right? You lose the diversity pressure because you have this communication. In this case, they're all independent entries, which means you have, well, it may all be wrong, or 90% of this is junk, but there is diversity in terms of uncorrelation of errors, unless they all went to the same school or use the same book, right? But the chances of diversity is much higher here. So what I'm saying is I could use maybe 1,000 of these 9,000 models to do a lot of good, better than just using the best model. And this leads to the concept of fusion, which is my third point. Any questions so far? How much time do I have left, Mario, so I can skip? 10 more minutes? Okay, I have 22 minutes elapsed, so I'll aim for the 40 minutes. yeah, what about my job? Because I care about my job. And I said, really, when I was young, you can tell by the beard, the length of the hair, the plenty of hair and the lack of any white hair or white beard. When I was a knowledge engineer and AI was at its peak, right? We were doing knowledge capturing through sessions called knowledge engineering sessions. And then we handcrafted intelligent systems that contain the domain knowledge. This was actually the locomotive expert, was my very first expert system. And that was a very interesting, challenging, painful, time-consuming job, which gave me great job security, right? Because then I was the only one who could maintain that system later on when people want to change. Okay, move it by 10 years, and it's still the same problem. I'm now the magician. I'm sorry, this is what I want to show. Think of this as the scientific method. You have some experiments that eventually seem to validate a theory. You formalize it. You then put some assumptions and limitations, so you capture that theory in a tool. So this was neural network backpropagation. This is a MATLAB neural network tool, and you have a license, right? It doesn't make you an expert in building neural network applications. You just have a license to it. So to create the application, you had to go through experiments during which you did the problem formulation. You did all the feature extraction. You figure out what was the context. You clean up your data. You say, okay, this is what I'm going to use for testing and validation. I do the design, validate it. If it works, maybe I can then compile it to get some throughput, and do I get the performance at the end? And if this didn't work, oh, I'll just keep running through this. What does this mean? Great job security again for me, right? Because I'm the one running the show. Unfortunately, I'm the bottleneck, right? I do not scale up. Remember, I tried to tell you the difference between building model by yourself, using maybe thousands of data points, and having now gigabytes or petabytes of data. It doesn't scale up, even with one model. What if I want to build 200 models? Not in my lifetime, right? Again, I'm trying to provoke you into thinking that it's time to shift gear, or getting ready to shift gear. So having done that, and this is another example where by using hot and T-squared, we also did the same with auto-associative neural network. I can pick some anomalies out of raw measurements that are getting the sensor data. So that was in the 90s. In 2000, it was a little bit better. It was a little bit better because I started using MetaHeuristics, like evolutionary algorithm, to start searching in the model design space, right? So the search was automated. I would still be intervening, but now at the meta level, trying to clean up the reference set that the MetaHeuristic was using. So I'm basically saying, over time, when we use this, for instance, to deploy an automated insurance policy underwriter, where when underwriters are trying to assess the risk of an applicant to determine the premium. But then you have medical knowledge advancing and telling you, you know what, it's not the cholesterol level that matters, it's the cholesterol ratio between good and bad cholesterol. And then you have new tests that were available. And then the government allows you to ask additional questions, which you could not ask before. So you have new inputs, you have new knowledge, you have to maintain the automated system you've deployed already, otherwise it becomes obsolete. It's not just the process of developing the system, it's the process of maintaining the system to avoid obsolescence. It's the life cycle of that process. And so if you use the process to generate it, all I had to do was go back to my evolutionary algorithm and edit the training set to say, would the decisions made in the past still valid now in the light of these new advances of science and knowledge that I had? And so basically by editing the output, not me, but three experienced underwriters on selected output, I could then say, okay, now I have a new target, evolutionary algorithm, find me the best algorithm for this new target, right? So I'm using now some tools to stay afloat, to cope with complexity of life cycle, modern life cycle, and I'm still employed, which is good, right? So this is an example of a digital underwriter that I just described. I'm going to skip it because I want to get to the last point, and so I call this is a curse of the cloud. I don't know. But at best, I'll be a part-time magician. Let me explain you why, and then I will quickly switch to the results of some experiments, and then I'll continue this insight during this roundtable to do some time management. We have seen already the concept of crowdsourcing, right? Amazon Mechanical Turk. Folded is an example in which a problem was casted in terms of a game, and the gaming community solved a problem that bioinformatics or biologists had not been able to solve with molecular folding for decades. Okay? And they did it for fame and glory. And I already talked about Kaggle. There are, and Innocentive, there are other tuned ID and crowd analytics, but again, they're sites where we're hosting competition of analytics model building against a particular requirement. So that's crowdsourced models. Outsourced models, okay, we still go out to major universities and fund them with, say, we'd like you to start working on these problems, and maybe you can come up with some models. In particular, we're working with MIT, and they're using genetic programming in the cloud to evolve a large number of symbolic regressors, which I'll be showing you in my results later on. So I use that as a surrogate for the Kaggle.com, right? Instead of having people submitting those entries, I have a GP in an island framework with a lot of diversity injected in it. So we have different function sets in different islands, basis function in different islands, and including different grammar, and different feature subset in different islands again. And then we had a Pareto between diversity and performance to get a very large variety of that. That's, I think I just mentioned, that iScale is our own internal way of doing, using differential evolution in model space to come up with tuning and optimization of different models and coming up with a large number of them. And finally, by the way, this is where I work. It's still me. Remember, the whole talk is about me, right? And how I'm becoming smaller and smaller. And we can develop, there are some techniques that we became reasonably confident and comfortable with, and we're developing models. But the point is, right, let me go to the next one. So this is me, and this is where I work. And with my colleagues, we can probably get up to 10 models, right, for a particular problem. Evolutionary algorithms in the cloud, hundreds of models easily. Outsourced models, maybe in the tens because still manual, but crowdsourced in the thousands, right? And this is using sort of a virtual version of me in the cloud to do model creation already in the cloud. So the point is now I can have thousands of models that are relevant to specific queries in the problem. And the query could be, read my data and tell me if everything is normal or something is abnormal. If it's abnormal, what caused it? That's diagnostic. From anomaly detection, we go to diagnostics. Tell me how much life I have left, remaining useful life. That's prognostics, which basically gives me a horizon for, do I have to take an action immediately for safety? Or if I have 2 weeks, how can I allocate my resources, change my future production and load? Maybe I can derate your load so you last a little bit longer. So then I can accommodate you within my repair shops and whatnot. Okay, so that's your optimization horizon. All this puts me out of work, right? So what I'm saying is, well, if you cannot compete with all these other guys, you ought to be putting some smart here in the cloud when you're doing service delivery. And that's where the remaining 8 minutes I have left, I hope, of my talk is. And I'm going to sketch this very quickly. Just the first two steps is, for each model, I have to create meta information. I have to tag the model and say, what is the sweet spot of this model? If this model was, let's assume it's supervised learning. This model has a training set. I need to know what is the hypervolume that contains all the points in the training set, right? Simply min and max on each of the feature space, or each of the features in the feature space. Then if you ask me a query, I can say, is the query inside or outside that hyper rectangle, right? If it's inside, at least I'm not extrapolating. But if it's inside and far away, I know that it may be a stretch to use those models. So, but I can do that without knowing which model it was, how it was built, who built it. I just need to know the pedigree of how it was built. And then the next one is, can I somehow capture the performance of that model in different regions of its applicability space? And the best way that I know of for creating this is using Hyperplays and a card tree, which is using the error that the model has made when it was used. There are additional steps to this, which I'll skip for brevity because they're not needed as much as these two. And I'll go to the experiments. So the first experiment was to say, we are trying to predict the load that a power plant can generate by burning coal. We want to predict the NOx, which is the emissions, that it would be generated with the settings required to generate the load, right? Because you bid on the load as a utility. And then, as a result, you have emissions, and you burn coal, and heat rate is just 1 over the product of the efficiency of your boiler and turbine, okay? So you want to meet the load, that's an inequality constraint. You have inequality constraining SO and CO, just want to make sure it's legal, nothing more to it. But then you have an optimization between NOx and heat rate because you want high temperature for efficiency, but with high temperature you have high NOx. And so initially we trained a 30 neural network using bootstrapping, and that was okay. And when I then used our methodology, it's easier to see the standard deviation of the error versus the MEM, the mean absolute error. These were all the 30 models. This was the average of those models. And these two were two different experiments for different granularity of the cut trees obtained by our method. This was for the load, the NOx, and the heat rate. So in all cases, we had some significant, statistically significant gains in both standard deviation as well as MAE. Then I told my MIT friends to say, hey, why don't you build me some symbolic regressions? And they did. We had somewhere between 36 and 47 regressors, each for each of the output. Again, they generate hundreds or thousands, but then we pick the Pareto of performance and diversity, and we only use those. And again, these were the models with the baseline of just the average of those models, and these were the results of our corrections with dynamic bias compensation and relevant weighting for load and NOx and heat rate. Again, pretty significant. And then I said, well, since I have them, let's put them all together. So now I had around 70 models. And again, the gains are not as significant as before. At a certain point, you saturate. It's like when you're running random forest, for those of you who are familiar with random forest. At a certain point, having 200 trees or 300 trees makes almost no difference. Right? But what was interesting was the fact that we were agnostic about how the models were put together. We just tag them the same way, so it had to be an agnostic way, otherwise it doesn't scale up, right? And so in conclusion, I think it used to be power to the people, but it's the power of people, augmented by collaboration tools, being able to cloud computing, and there is this very strong trend of intersect on 2 or 3 of these. I'll stop here because of time constraints, and I'll continue later on. Thank you very much.
Questions? Is that your hand?
No.
Questions?
Please.
I'm just curious about this crowdsourcing R&D you mentioned before.
Yeah.
How practical and realistic is it because of IP issues, and you mentioned that.
Yeah.
And you also mentioned that 90% of the people will probably send you some channel, only 10%.
Correct, and it's still flourishing. In fact, every other month I see new sites that are promoting this. So there's another one interesting called Stack Exchange, not stock, but Stack, S-T-A-C-K, exchange.com, which is basically a Q&A on scientific issues, right? Powered by the crowd. So you have technology, science. In science, you have theoretical computer science, for instance. And there are people posing questions, challenging questions. You have theoretical computer scientists participating to the answer. It's, yeah, typically you need a moderator, or like Wikipedia is a good example, right? Wikipedia was put together by a crowd. You still have some editors who eventually decide if something stays or goes, right? But still the crowd can then modify or edit the entry.
How would a company deal with ideas flowing from?
Oh, IP, by the way, is, in the case of Innocentive, if you submitted something, you have to guarantee that this, either you own the IP or is IP free. It's part of the term and conditions. In the case of Kaggle.com, when you're submitting, you're relinquishing the right to what you submitted, assuming that you get paid for it. Now, how do companies react to people in their company participating outside is up to each company. And what do they find conflict of interest, and how do they find what's in your head and what you do in your free time. It's more of an HR problem than a technology problem. Yes, Gary?
Yeah, Piero, this is the first time I heard about this cloud outsourcing, so please forgive my ignorance. What you mentioned that all this data, the idea that provided, I think it's all being checked and validated by the moderator. That's the only mechanism?
It's not the only mechanism, but sometimes you want machines to validate it. For instance, at Berkeley, they're just looking at the bias in the crowd, and can I use machine learning to remove that bias? It's a very flourishing area of research.
What is the catch for anyone to contribute their IP into this process? Why is anyone would love to respond to it?
There are many motivations, as I said. Fame and glory is mostly a recognition. Why do we put so much volunteer time in IEEE?
Yeah.
Right? It's not for the money.
That's for sure.
It's an example, but.
Interesting, yeah.
Okay, thank you very much.
Thank you very much.
Great talk.